So I'd like to introduce Matthew Taylor from Doulos. He's a senior member of technical staff, and today he'll be talking about an introduction to verification and SystemVerilog for beginners. So over to you.
Thank you very much. Well, thank you very much for coming, and thank you very much for those listening online. So my name's Matthew Taylor. I've been working for Doulos, who we do technical training courses in verification, which is what we're here today, and various other areas that you'll see a small advert at the end. I've worked for Doulos for 10 years and a week. And before that, I worked for Sony doing chips for digital TV and mobile phones. So that's my background. So this is a tutorial. Please, welcome, please come in. Yes. So those online, there's a few more people coming in. So this is a tutorial paper. That's a grand word, isn't it? It's a tutorial presentation. Really, I guess, aimed at those of you who may have sat through some of the presentations in the keynote and thought, what is he talking about? What's UVM? What are all these things that are not going to be used in the future? Welcome, come in. We're aimed at for people who perhaps didn't follow everything that was said earlier this morning. So I'm going to talk, there's two parts to this really. We're going to talk mainly about verification in general, and as it said in the abstract, the landscape, the different techniques and languages and various other things that are available for doing verification. And then right at the end, introduction to SystemVerilog. There's about, I don't know, 5 slides or something like that. SystemVerilog is a huge language. So it's not good for people online, for me being waving physical things around. It's a huge language. It takes, we run a training course that already assumes you know Verilog, and it takes 5 days. And we've got about 15 minutes. So, I mean, if you are coming hoping to learn SystemVerilog, I'm afraid you're going to be sadly disappointed. What I can do is give you a taster. I can show you what SystemVerilog's, very small amount of SystemVerilog, what it is, and how it relates to what I've been talking about in the first bits of the presentation. So what's verification? And this was touched on in Andy Bond's presentation this morning. Verification is checking that your design meets the specification, or another way of putting it is meets the previous stage of the design process. So checking that your RTL, your design, meets the specification, checking that your gates do the same thing as your RTL, and so on. And it says here in this sort of definition that we got on the side, contrast with validation. That's really, really important. Something else that Andy Bond was talking about in his presentation this morning, because it's no good if your design meets the spec and the spec's wrong. Been there, done it, talk about it in a couple of slides time, your chip's junk. The chip was junk because it met the spec was wrong. So there's various bubbles on this slide, and these are some of the topics that we're going to be talking about. So under the topic of verification, there's different techniques, different languages, and so on. So the workhorse of verification is simulation. So we're certainly going to be talking about that. We're going to be talking very briefly about what are called properties. So these are rules that you can write. If this happens, then that should happen. And you can simulate those, or you can formally prove them. You can mathematically prove that your rule has not been violated. There's also hardware that can help you. So big boxes of electronics that were talked about this morning that need special power supplies, or used to need special power supplies at FPGAs and so on. And then at the bottom here of the slide, there's various techniques that we're going to be talking about. I will talk about those when we get onto them, rather than delivering the entire presentation standing in front of this one slide. So here are some of the languages that you might use for verification, and you can see there's lots of them. So starting at the top, it says the list has not changed for years. And that is true. People, when I say I work for Doulos and I teach people to design silicon chips, and they say, how on earth do you keep up with the technology? And I say, well, you know, the languages I teach were invented in the 80s, some of them. So starting with VHDL, invented in 1987, I think, quite a rigorous, strict language, often used for FPGA design, particularly in Europe and military stuff. Quite abstract, but not super abstract. Underneath that, we've got PSL, which is property specification language. It's actually part of the VHDL standard now, and that allows you to write the kind of rules that I was just talking about. If this happens, then that should happen. Then there's Verilog, which is a sort of rival to VHDL, if you like. It's slightly lower level, slightly less abstract, tends to be used outside of Europe for FPGAs, or used, and for IC design anywhere on the planet, really. But its successor is SystemVerilog, and that's in red because that's what we're going to focus on for the last 15 minutes or so of this presentation. That's vastly more powerful than Verilog. So if you come on one of our training courses, we will give you what we call a golden reference guide, which is like a reference book to the language that you're learning. The SystemVerilog one is about 3 times as thick as the Verilog one or the VHDL one. Yeah, it's just a huge, huge language. Here's another language, E. So that was mentioned this morning in Andy Bond's presentation. Specman is another name for it. Not exactly sure whether it's Specman E, Specman E. It's this verification only language. So really quite an abstract language, very serious software. As was mentioned this morning, designers don't like it because it's completely different to Verilog and VHDL that they're going to be using for doing their design in. And then at the bottom, we've got various software languages that you can either use, in the case of C++ and System C, you might use for modeling your design in a high level abstract way, or generating inputs for your test. And then the final category at the bottom, various what you might call scripting languages. So you might, well, Python, to be honest, and Perl I've used for actually generating stimulus and doing checking and that kind of thing. Stimulus is inputs for your design. But you could also use them for controlling which tests, which simulations are being run. If none of this is meaning much to you, yeah, it will do in an hour's time, or I'm not doing my job properly. So there's various approaches to verification, and this is not in any way any kind of comprehensive list. And you know, there are other things that we could talk about as well. And these techniques that are going to appear one by one are not mutually exclusive either. You know, we're not going to pick one of these. We can do a variety of these combined. So, you know, basic one, if you're designing an FPGA, I'm assuming everyone knows what an FPGA is, a programmable logic device. If you're designing one of those, then you could just program it and go into the lab and connect it up to the rest of your electronics. Pretty dumb thing to do, but people do that. Doesn't mean that you shouldn't do it at all, of course, and I'll talk about that in a second. Really, the very minimum you should be doing is writing some kind of basic test bench. So this is, you've got your code that is your design, and then more code that at the very least generates inputs to your design. And because just programming the FPGA is rubbish, because you can't very easily control the inputs to your design. You can't very easily observe the outputs. If there is a bug, you might not spot it. And you know, it's just a very poor way of doing verification, but it's an excellent way of doing validation, as I'll mention in a second. So something else that you might do is use some other software language. So Python to generate stimulus. You might have a high-level model of your design written in C++, MATLAB, whatever, some other software language. You might use what's called transaction level modeling. So I need to explain what a transaction is. A transaction is a high-level thing that your design can do. So a very simple example, let's suppose your design was a memory. What can a memory do? Well, you can write to it, you can read from it. There are two transactions. A CPU, what do CPUs do? They execute instructions. So again, there's a transaction, a jump instruction, a branch instruction, a load instruction, whatever it is that your CPU does. And so the thing is with transaction level modeling is you keep as much of your it's more abstract, and you keep as much of your test bench as you can at this abstract level, because it makes it easier to generate inputs, stimulus, and it also makes it easier to check that the design is doing the right thing. So more on that story later as well. Something else you can do, and this has been mentioned already today, constrained random. So generating random inputs to your design under test. And I don't mean completely random inputs. It's not like infinite monkeys with infinite typewriters, because that's going to take a long time to generate anything useful. What I'm talking about is a random stream of sensible things to do. What's a sensible thing to do? A transaction. Random transactions, random valid reads, random valid writes, random streams of CPU instructions, random packets, whatever it is. You can then use acceleration emulation. So those are big boxes of electronics that, well, you used to buy. We used to have one in our lab. I don't know if it needed a special power supply. It did need a special floor, strengthened floor to put it on. But I wasn't involved in that personally. What I've been involved in a lot is FPGA prototyping. So my background is designing chips. And if you get a chip wrong, it's very costly, as I'm sure you can imagine. And I mentioned a validation failure earlier. Chip met the spec was wrong. So after that, we always did FPGA prototyping. We always got our digital TV chips and put them, connected them up to test gear in the lab, put them in the back of a van and drove them around the countryside to check them before we committed to silicon. And if you're designing an FPGA, you can't prototype it, because what would you prototype it with? But that goes back to the point at the top there, just programming the FPGA. If you remove the just bit from that sentence, then programming the FPGA is very valuable. And that's the validation part of it. It's no good your design meeting the spec if the spec's wrong. But we're talking about verification today, verification features, beginner's guide to verification, etc. Something else really cool technology, formal verification. So this is mathematically proving that your design is correct, basically. If mathematically proving that your design is the same as another design, so your RTL is the same as your gates, for example, or mathematically proving that your design meets those rules that I've mentioned already. So you might call those properties. Well, you do call them properties. So mathematically proving that if this happens, then, let's give a more concrete example. If there's a request, then there should be a grant within 10 clock cycles, mathematically proving that that always happens, that there's no circumstance where that would never, ever happen. As you can imagine, I'm sure if you've ever done, dipped your toe in the water about what I'm talking about now, really, really powerful technology. Final one on this list, and as I said, it's not comprehensive completely, it's not mutually exclusive either, but portable stimulus. Portable stimulus is really cool technology. My ex-colleague, only because he's retired, John Ainsley, one of the founders of Doulos, describes this as constrained random on steroids. What's the difference between this and constrained random? Well, a constrained random would be, think of the designs they were talking about this morning on the screen with zillions of CPUs and network this and modems and blah, blah, blah. You might, and again, Andy Bond, he was talking about verification. He touched on this. You might think of a test where you're sending data from one CPU across the bus to one memory or something like that. Meanwhile, you've got some data coming in over your 5G modem that's going across the bus to some other CPU, etc., etc. What PSS is you describe your design in a abstract way. So you say, here are all of the data sources, here are all the data sinks, only 3 of them can work at once, and this can't happen when that happens, this can't happen until that happens, this can happen at the same time as that, but only when this is finished. And you give it all sorts of rules like that, and what it does is it goes and writes the test itself. So randomly generates different scenarios like, oh, let's try sending data from this CPU to that network interface and at the same time from the camera to the, etc., etc. Really, really cool technology as well. Interestingly, doesn't seem to be being talked about today. I've not seen anything in the program about it, but very cool technology. And as it says here at the bottom, the further where you get down this list, the more specialist it gets. So, the designers would be perhaps doing their own verification just to check that it's sensible and so on. Or if it's a small project team, they might be doing their own verification as well. But the further down you get this list, the further down you get on this list, the more specialist it becomes. So here's a sort of classic diagram, lots of sort of academic type sources would show you this, but it's just showing that verification is checking that your design is the same as the previous stage, where the previous stage may well be the specification, but it doesn't have to be. But please don't forget validation, as Andy Bond was, I keep talking about him, don't I? Andy Bond said it's important, as I have tried to convince you this morning, it's important. So you do need a plan. I'm not going to spend much time on this, and perhaps something I didn't say, if you are following the slides in the book, which I can see 1 or 2 of you are, there will be some missing because I've got too many slides to fit in the time, so I've deleted about 1/3 of them. And if you see a little red spot, it means don't spend too much time on this slide, Matthew. So you do need a plan, and there are all sorts of automated ways of generating and maintaining and following the plan that Andy Penrose was talking about earlier. Of course, you need a higher level plan. Am I going to use SystemVerilog or VHDL, or there's something called UVM, which we haven't mentioned. So I'm doing a talk this afternoon where I'm going to introduce that. That is a way of using SystemVerilog to do verification. Am I going to do an FPGA prototype? Am I going to use emulation as a service from one of the EDA vendors, etc., etc. And this was also talked about this morning, that the sort of trade-off between accuracy and time. So simulation is highly likely to be the backbone of your verification. Yes, you might be doing formal, you might be doing FPGA prototyping, etc., etc., but a significant dominant part of your verification efforts is simulation. And there is a trade-off between accuracy and time, basically, which was talked about earlier. So mainly what I'm going to be talking about in this talk, and the one I'm doing this afternoon, really is what's called RTL simulation. So it's simulating the design that you actually type in. But you could simulate more abstract models, done a lot of that. So a digital TV chip, you can't just design the details of millions of gates of DSP by writing RTL. You need something more abstract. We use C++. Similarly, you need to do more detailed simulations as well. So what do you do when you simulate? Well, there's one main job of simulation is supplying the inputs to your design, the stimulus. The other main job is checking the outputs, and you really should be doing your test code should be doing those things. And there are two ways really of generating inputs to your design. We've already talked about the second one of those, constrained random, where you don't put noise into your design, you put this stream of sensible things. The other one is what's called directed testing, where you create the stimulus yourself. And it's highly likely that you're certainly going to be doing the first one, but if you're doing the second one, you'd be doing both. You'd either write some random tests. Let's just try some random things. But there's some certain things that you need to be able to test that it's much easier to just write the test yourself. Or you might want to put your design in a certain mode. There's no point in testing mode 3 if you haven't got some directed stimulus at the beginning of your test that puts the chip into mode 3. If you assign the mode randomly, whatever that means, you're wasting your time. So what you're going to need if you're doing simulation is a test bench or a test environment. So this is the code that has certainly one job, as I've already said, which is supplying the inputs to your design under test, but really should have two jobs, the other job being checking the outputs from your design under test. Design under test, DUT, dot. That's what that means. So that test bench might be written in the same language that your design is done in. That's very common. If you're designing in VHDL, you would very commonly write the test bench in VHDL as well, or Verilog, but it doesn't have to be. So I've already mentioned SpecMini. You can't do your design in SpecMini, any more than you can do it in French. You can only use SpecMini for doing the testing. So if you're using SpecMini to do your test bench, your design would have to be in some other language. If you're designing in VHDL, though, there could be a lot of benefit in using SystemVerilog to actually write your test bench. Why? Because SystemVerilog is much more powerful than VHDL for doing testing, and because that is a language that is quite standard across the industry. So there's a lot of benefit that you can get, verification IP that was mentioned earlier, and so on. And the nice thing about verification is you can use the whole of the language. So I don't know what your levels of expertise are, nor certainly not the people listening online, but you will be aware if you've done any design that you can't just synthesize anything. There's a subset of the language that is synthesizable. But whereas with your test bench and your test code, you can use the whole language. And if you're using SystemVerilog, well, you get to play with fancy object-oriented stuff, which if you're an engineer that likes playing with new things, that's going to be of interest to you. So here's a basic test bench. So the very minimum, as I've said a couple of times already, is it needs to generate inputs. And you could just generate them in a very simple, low-level way, as this code in that little box implies. At time 10, drive this input to this value. At time 20, drive that input to this value. At time 30, check that this output is equal to that value, etc., etc. And that's fine. It's quick and dirty. It might be the kind of test bench that you write to check your design before you hand it over to a specialist verification engineer or team or whatever. You obviously need to then be checking that your design is doing the right thing. You could just look at waves in a waveform viewer, but that's pretty dumb, really. Might be okay for just checking your design is sensible, but it certainly isn't okay for verifying your design really is correct. Your test bench needs to be checking the outputs of your design under test, because looking at waveforms is error-prone, tedious, time-consuming, not repeatable. Whereas if your code in your test bench is checking the outputs, you can review that code. Once you're happy with it, you're confident that it's working, and so on. But the disadvantage of many disadvantages, but a key disadvantage of this kind of test bench: quick to write, quick and dirty, very hard to maintain. You make some small change, and the output that was supposed to come out at time 1, 2, 3, 4, 5 suddenly comes out at time 1, 2, 3, 4, 7, and your test fails, and you've got to constantly edit your code to keep it up to date. Whereas if you have what is called a structured test bench, you're going to find this better in many ways, including the problem that I've just mentioned, keeping the test bench maintained. So what we mean by a structured test bench is a test bench made out of different pieces, different components, and I don't mean VHDL components, different pieces that have specialist jobs to do. So some of them are more obvious than others on this diagram. So here it says stimulus generator. That's pretty obvious what that does. It generates stimulus, but not as ones and noughts. It's not just waggling the pins on the design under test. What it's doing is generating a stream of transactions, which may or may not be random, and they are represented in whatever language you're using to encode your test bench as some abstract software-y construct. So if you were using VHDL, you might use record types. If you were using SystemVerilog, you might use something structs. You might not know what all of these things are, but I'm hoping you might know what some of them are. You might use structs, or you might, really powerful, you might use classes. And I will talk about classes when we get onto the SystemVerilog part of this. So you've got some high-level abstract software-y thing coming over here. And then, of course, your design doesn't understand high-level abstract software-y things. And so you need a component that translates the abstract software-y thing into the actual ones and zeros that the design actually understands. And there's a pretty, as also mentioned this morning, a pretty standard name for that now. We would call that a driver. So that the input is a VHDL record type, a SystemVerilog class. The output are the ones and zeros that the DUT understands. And then other pieces on this diagram, we've got a monitor. The monitor is an opposite of the driver. So the monitor is observing the ones and zeros that are going into or out of the DUT and converting them back to some abstract software representation again. So transactions. And then you can see we've got various blocks hanging off our monitor there. Key one, the checker, the one that's checking that the stream of transactions coming here is correct. And quite often it's easier to check that a high-level transaction is correct than checking the pins of the design directly. Take the memory example again. If you've got this low, just going to flick back a slide. If you've got this low-level type test bench, and I've already mentioned the problem with that, if you want to check the read data coming out of your memory, you need to check it at exactly the right time. Whereas if you've got the kind of test bench that we've got here, the monitor can observe that a read has happened. The monitor will observe that there was a read of data 1, 2, 3 from address 456 at time 789. And we don't care what time it happened, so ignore that. There's data 1, 2, 3 from address 456. And the checker can, say, okay, well, what was the corresponding write? What did we write to that address? Well, we wrote 1, 2, 3. Okay, it works then. Hooray! There's an example of why it's easier to check at the transaction level. And there are various other pieces on this diagram. The key point here, I'm already, hopefully I'm selling it to you, is that each one of these components, these pieces, has a specialist job to do. And one of the advantages of that is that it makes it more reusable. So UVM was mentioned already, how to use SystemVerilog to do verification. If you're interested, come along this afternoon. UVM is like test bench Lego. This is test bench Lego, how to come up with reusable pieces, each of which has a well-defined job to do to make your test bench. And hence you can create your test bench with less effort and reuse the considerable amount of engineering time that you've put into your test bench, again and again and again, more easily. So one of the key difficulties, one of the key jobs that your test bench already has to do, which I've already talked about, is checker. So how do you write a checker? And this is like the $64,000 question, because it's not easy, frankly. It might be easy. It depends on the design you're dealing with. If you have a garbage in, garbage out sort of design where you put something in one end and the same thing comes out at the other end, reasonably easy to check, but that probably isn't the case. This diagram is showing a way that's easy to visualize, not necessarily easy to implement, but easy to visualize how to do your checking, where you have some kind of way of calculating expected results, which could be like a high-level reference model of your design. And you might not have one of those, but you might have one of those. So designs I've worked on, this has already existed because we couldn't have got as far as writing the RTL if we hadn't have done a lot of the design work at a more abstract level already. So what you do, basically the principle is you apply the same inputs to your design under test and your high-level model, and then assuming that exists, the checking is trivial because you just compare the two. But you do need one of those. You might be simulating that at the same time. What I've always done actually is run that beforehand, because the kind of designs I've worked on, the behavior of the test bench, the generation of the stimulus doesn't really depend on the DUT. So you can generate it in advance and just squirt it in. And then our high level model knew what the outputs of the DUT were supposed to be. So something that I've mentioned already is constrained random testing. So why might you do that? I haven't really talked about that. And the answer is mainly because it thinks of test cases you haven't thought of. So thinking of the memory again, you could think of a test for a memory. Okay, let's write something to an address and read it back. That's a pretty dumb test because a capacitor will pass that test. Your bus might just remember what you wrote. Okay, better test. Let's fill up the memory full of things. Let's write 0 to 0, 1 to 1, 2 to 2, 3 to 3, and then we'll read it all back. Okay, better test. But what if there's a bug in your memory where you read it and that changes the memory location that you've just read for some reason? So the test that I've just described, that's not going to find that bug because you only read each location in your memory once. Whereas if you read again, you'll discover the bug. If you, instead of filling up the memory, you randomly chose whether to read or write, and you wrote random data to a random address, the bug that I've just described, you will hopefully find. So there's a very simple example of why random testing is better than, or not is better than, but should be done as well as so-called directed testing. Another one is you can just set it running and it can be finding bugs. If you've got enough licenses and enough computers, you can just set it running and off it goes, and it might be doing useful work. There are some more things to say, however. One thing you do need if you're doing random testing is an automatic checker. You need a stimulus independent checker. Your checker needs to be able to check that the design is doing the right thing, whatever you throw at it. And the diagram that I showed you on the previous slide is an example of just that. The next thing you need to do, and we're going to talk about this in a minute, is you do need some kind of metric, and that word was used this morning in Andy Bond's presentation. You need some kind of metric to know when you finish testing. Because if you're just throwing random stuff at your design, how do you know whether you've tested it properly or not? And the answer to that is to collect something called functional coverage. And we'll be talking about that in a few slides' time. So basically, functional coverage is as a checklist of all of the things that your design needs to be able to do. So take the memory example again. Have you done a read? Have you done a write? Have you done a read from a location you previously wrote to? That would be the absolute minimum of things that need to have been generated randomly for you to know whether you've tested your design or not. If you had a CPU, have you tested all the instructions? Have you tested combinations of instructions? Have you done long jumps, short jumps, backwards jumps, etc., etc. Obviously, a real design, that's going to get quite complicated. So that's a key part of it. And then the next thing is, what do you do if you haven't got 100% coverage, if there are things that haven't been tested yet? And there's an iterative process now. There's a feedback. So you run your random tests, you discover you haven't tested everything, you need to decide what to do next. And that could be running the test for longer. So just run the test for twice as long. And you probably will get what's called better coverage. More things will be tested, but you'll probably still have what are called coverage holes. So what you would then look at is perhaps, why have I got this coverage hole? Oh, it turns out that I'm never generating this kind of CPU instruction, or I'm not accessing that part of memory, because basically the probability of that thing being generated is too low, or possibly literally zero. And so you would change the way that the random stimulus is being generated. So you've got this iterative process going on here. And the reason why it says constraints there is because when you're generating random inputs to your design, I've already said this a couple of times, you're not just generating noise, you're generating a random stream of sensible things, transactions. And the difference in the space from which you're choosing your inputs between noise and transactions is that the transaction space is smaller, it's constrained. You don't want to generate one of those, because that's nonsense. You don't want to generate one of those. That's nonsense. I want to generate only the sensible things to do. And so you might get the way that you've constrained that space wrong. And constraint is actually a keyword in the SystemVerilog language. So we'll see this before the end of the presentation. I wonder how I'm doing. Unfortunately, it's too small to see. I think I'm behind, so I need to speed up. So we'll see that. So a little bit about coverage. There are two kinds of coverage. There is code coverage. Code coverage is, that's wrong. There are more than two kinds of coverage. Here are two kinds of coverage that I'm going to talk about. Code coverage is, have I executed all the lines of code? Have I executed all the if statements? Are they true or false? All the different paths through the code? Have the variables taken all the values? This kind of thing. And this is what's called, is necessary but not sufficient. If there's some lines of code that you've never executed, you clearly haven't tested your design properly. But just because you have tested all the lines of code doesn't mean that your design is right. That's relying on the checking as well. So that's called code coverage. That has been around for about 30 years now, I should think, at least. Then there's also what's called functional coverage. And functional coverage is what we were talking about just now, is checking that your design has been tested properly. And in some ways, it's quite similar to code coverage, but you're focusing on the values that variables have. So this is a little bit of SystemVerilog here. Well, it's two lumps of SystemVerilog. And the first one is a little bit of what's called a class. And this is just might be describing a transaction, and we'll talk about that later. The bottom one is what's called a cover group. And a cover group is a container of something called a cover point, and a cover point is a probe. And what we're doing is we're probing these two variables, opcode and mode, and we are keeping a record of what values they have taken in any simulation. So not just one simulation, across all of our simulations. And what we're looking for is missing values, basically. So, if the design really were a CPU, then we do want to check that we've tested all of the opcodes. And you wouldn't actually see a histogram like this in any EDA tool, but you think of histograms like this sort of conceptually, and the number of opcode 4s executed in any simulation is 0. We haven't tested opcode 4 properly then, have we? And so we need to then go back to our stimulus and find out why that's the case. Is our test bench wrong? Have we just not run the simulation for long enough? Whatever the reason is. So here's a diagram of what's called state space. And this is like an introduction to the idea of formal. And the reason for showing it is that, the state space is all the different combinations of 1s and 0s that the flip-flops in your design can have over time. And it's suggesting that random tests are better than directed tests. But, you cover more of the possibilities, more of the so-called state space. But leading on to this idea of formal is a mathematical proof that your design works under any circumstance, 100% state space coverage. And how cool is that? Really cool. Why do we bother with simulation at all? I'll explain this afternoon in my tutorial this afternoon. What this last diagram is showing is what happens when formal. You can't prove it, because guess what? You can't prove always. Well, usually you can't prove your entire design is correct. Who'd have thought? And so you then need to adopt techniques to get useful information out of your formal tool. Do what you can effectively, and that might be doing what's called a bounded analysis, where you're checking some of the state space, and then the art of doing that would be to, the engineer has to judge, have I checked the right bit of the state space? So formal verification, I've just been talking about this really very quickly. So really cool. You don't need to write the stimulus. You might need to write some rules, however. So we're going to talk very quickly about two kinds of formal. One is property checking, where you write the rules, and the other is equivalence checking, where you compare your design with another design, basically. So the rules are probably written in a language called SVA, and we'll see an example in a minute. That is SystemVerilog assertions. So here's this same diagram that you saw about 20 slides ago, and just showing you that the property checking idea, comparing your design to a bunch of rules, is something that you would be probably using to compare the design you type in, the RTL, with the specification. So you basically write those rules to encapsulate the requirements in your specification, and then you might be using equivalence checking for the next stages of this verification waterfall. So here's an example of a rule, a very simple rule: assert that output 1 is always greater than output 2. Assert that the address is always less than, is always in this range, that kind of thing. But the vast majority of your rules are going to be more complicated than that. And they're going to be along the lines of, if this happens, then check that happens. So if input 1 rises, check that output 1 is greater than output 2 after 2 clocks. And you would encode this, as we will see very shortly, in this language called SVA. So the next thing to talk about is SystemVerilog. So let's just spend 15 minutes or so looking at SystemVerilog. So what is SystemVerilog? SystemVerilog is the world's first HVDVL. The words only HVDVL. It's both a hardware design language, you can do your design in it, and it's a verification language. So it has a lot of the functionality of Specman E and other similar languages that were around at the same time. It's an IEEE standard. It was first standardized in 2005, and back then there was a separate Verilog standard, but then they merged to form one standard. So since 2009, Verilog is like an unofficial subset of SystemVerilog, and you can see it's been regularly updated. It's pretty well supported by the EDA vendors, better supported than VHDL. You know, it's only in the last few years that VHDL 2008 has had good support. You can certainly, you know, Verilog 2012 has been supported ever since I've worked at Doulos. There's not huge changes in 2017 and 2023. So, but that, you know, that's not so key. It's a huge language, as I've already said. You know, the what we call our golden reference guide, and if you would like one, we have some on our stand, but you do need to tell us who you are. That's the deal. The golden reference guide is about 3 times as thick as the VHDL or the Verilog ones, and that you can break the language down into different sort of areas, if you like. So there's SystemVerilog RTL, doing your design. It's not massively different to VHDL, to be honest, a little bit more powerful, but you're constrained by what your synthesizer understands. Your synthesizer can only synthesize RTL, whatever language it's written in. So there are some cool features, but you know, I wouldn't say any more than that. Then you've got this language called, it's like a language within a language called SVA, SystemVerilog Assertions. That's for writing the rules that I've been talking about, the so-called properties, assertions. We'll have a look at that in a minute. And then there's loads and loads of stuff for your test bench. So there's class-based stuff, object-oriented stuff, and we'll see why that's useful for verification in a second. And there's also a load of other stuff for verification that isn't class-based. So lots of stuff to do with randomization, lots of stuff for coverage that we've just seen, for example. So here's diving down another level. So, you know, there's cool features for RTL, so and general programming. What we mean by that is the sort of the kinds of things that other languages can do as well, maybe in your test bench, maybe in your design. So different, there's enums, which VHDL has had since 1987, structs, you can define your own types, other cool things, which I don't have time to go into at the moment, like pack structs. It has packages like VHDL has something called an interface, really cool for doing your design and for verification. There's your SystemVerilog assertions. We'll see an example in a minute. And then here's these various things that you can use for verification. So there's something called a clocking block for synchronizing your test bench to your design, object-oriented programming, lots of stuff about randomness, collecting coverage, and then all sorts of abstract sort of software constructs like dynamic arrays, queues, and all of the things you can see there. And then something else that's really cool, there's something called the DPI, which is an easy way to call C from SystemVerilog. So you've always been able to do that in Verilog, but it was hard. The interface was called the PLI and the VPI, and it was really for EDA vendors to do their kind of stuff. And so if all you wanted to do was call a bit of C, it was hard work. Whereas the DPI, it's really easy, really, really easy. So I've got about 3 or 4 slides now just showing you some examples of SystemVerilog. And really, they're just examples of the kinds of things we've been talking about in the last 50 minutes or so. So here is an example of SVA. Here is an example of something called a property. And, you know, as I've said, SystemVerilog is a 5-day course, so I can't really teach you SystemVerilog at all. This is a taster. But here's an example of a property. So here's this fairly abstract thing called a property. And what this is saying that if ACK rises, then, and this operator here is called an implication operator, and it's a really, really powerful operator. And it says if the left-hand side is true, then the right-hand side should be true. So if ACK rises, if there's an ACK, then within 5 clock cycles, there should be a ground. And that's a fairly abstract thing, And this second line of code here is what's called an assertion, and that is asserting that this property is true. So it's saying on the, we'll do everything on the positive edge of the clock, and that name there's that name there, that must be true. And so you could simulate this, and basically if that ever is not true during any simulation, you'll get an error. Or you can run one of these formal tools and prove that it never doesn't happen. How cool is that? Really, really cool. Not a panacea. You'll find out why this afternoon if you come this afternoon. Here is some more SystemVerilog. Here we have a class. So I can't really teach you object-oriented design in the 10 minutes that I have left. So here is SystemVerilog's interpretation of a class. And the key thing here is this particular class is representing a transaction. So it's some kind of bus transaction, as the name suggests. And so our transaction has a direction, and you can see this type here says, if you look a few lines up, it says read or write, and then it has an address and a data. So you can see there's some examples of type definitions in SystemVerilog. And then here we have a function that's bundled up with the class. If you know object-oriented design, you'll know that that is a method. And this particular one displays the transaction in a human readable way. And a real transaction would have other methods. Perhaps you'd want to copy your transaction or compare it with another one and so on. So you would write lots of methods in your class, and then that's why object-oriented design is useful for representing transactions. And then notice that this class declaration is in a package. So if you know VHDL and you know about packages in VHDL, there is one in SystemVerilog. Here is something that SystemVerilog has that other object-oriented languages don't have. E has them, but others don't. And that's labeling a data member as randomizable. And so that then means that the language has an automatically generated method called randomize that assigns random values to these data members. So that's how the randomization is done, much better than just generating random numbers. And you will see in a couple of slides' time how cool that is. Something else we've got here, if you know about object-oriented design, this function new in the middle there's the constructor. So that's how SystemVerilog does constructors. And you can see in this particular one, we're assigning an ID. So each of our transactions is going to be assigned a unique ID when it's created, when it's constructed. How do we know it's unique? Because we're keeping track of it. I can't explain what a static data member is. If you know object-oriented programming, you'll know what's going on there. But the key point here, that what's unique to SystemVerilog, or more or less unique, is being able to have random data members. You would use your SystemVerilog to not only create, SystemVerilog classes, not only generate your test bench, but to generate your transactions, to represent your transactions, but also to generate the other components in your test bench as well. And we'll see an example of that in a minute. The TV will turn off by idle shortly. Is there something? Can you push a button on the remote control or something?
Yeah, speak something.
I think you need. Is there a remote control that you can push volume or something, please? Thank you. You've moved focus from the PowerPoint because the clicker's not working. It's all right. You could click on the PowerPoint. Thank you. So, as I was just saying, you would create objects, zillions of transactions at runtime, and we're also using a SystemVerilog class to represent or to create test bench components. So we'll have a look at that in a minute. And this SpecManE language has two different kinds of classes for doing that, but in SystemVerilog, they're all the same one. So here's an example of a component made out of a class. So we talked about drivers many slides ago. That's a component that takes in a transaction and converts it to the ones and zeros that your DUT understands. So here we've got this thing called a virtual interface, which is a pointer to the design under test. Here we've got what's called a task, same as in Verilog, procedure in VHDL. The input is our bus trans class object, and you can see that this code here is looking inside that and driving the information from inside the transaction onto the DUT. So it's unpicking this abstract thing called a class and driving the DUT directly. Maybe there's a volume control here on the back somewhere. I used to work for Sony, but anyway, I don't know this TV. Here's why having randomizable data members is really, really cool. Because as I already mentioned, constraint is a keyword in SystemVerilog. So here is a construct called a constraint. And can you see that we've related the values of these data members together? So instead of just generating completely random values, we now have a constraint that says, here's the implication operator again, if the address is less than this, then the direction is just a read. And this would be for the situation where you had a memory map where the low, whatever part of the address map it is, the low part of the address map was read only. So it's not generating writes to that part of the memory map. And I think the final slide on SystemVerilog itself, the next thing you would do, object-oriented programming gives you what's called inheritance, where you can, instead of adding that constraint to the original class, what you do is you take the original class. Unfortunately, we can't see it here in the office, in the room. You folks online have an advantage here. We've got a message come up on our screen. What it's saying is class memMapTrans extends busTrans. This is a really, really powerful concept, because what we're doing is we're taking this quite project-specific thing called a constraint, and instead of making the original transaction project-specific, we are creating another project-specific transaction. And what is really, really, really cool is all of the code that we wrote to work with this class busTrans also works with this new class memMapTrans. So you can write your test bench in SystemVerilog to work with a fairly basic transaction, and it will also work with this specialist transaction as well, either because you want to do a different test or because you created the test bench last year for a different project and you want to reuse it. So it improves reuse as well. So last two slides, a couple of adverts now. First one, EDA Playground. This is a website that Doulos owns, my employer. I'm actually the person that looks after it. So if you've got a problem with it, buck stops here. It's a really cool tool. It allows you to enter code. Oh, you've lost the screen. It allows you to enter code automatically. Enter code online and then run simulators. All the big simulators are there, and some free ones as well, and a couple of synthesis tools. It's really cool for experimentation, because you don't have to find a license and open text editors and plots on server farms or whatever. And then the final advert that you can't see is, I work for Doulos. Our business is training. That's what we do. We run training courses. The relevant ones to you guys here would be Verilog, VHDL, SystemVerilog, UVM, Formal, but we also do embedded software, AI, automotive, Linux, and various other things like that as well. So I don't know whether anyone has any questions. I was aiming for 50 minutes and I've taken 60. It's always the way, isn't it? Are there any questions, or is lunch more exciting? Are there some online? Okay.
I don't know the number of clocks that grant.
Okay, so this was relative, I assume, for the where we were saying if there's an ACK, then the grant should occur within 5 clock cycles. So really good question. You can in SBA say a grant should occur eventually, and if you learned, did our SystemVerilog course or our formal course, we would explain why that's dangerous. So you might want to do some kind of high-level simulation to put a high, an upper limit on it. Perhaps should occur within 1,000 clock cycles or 100 clock cycles, because what design can you actually wait forever, literally forever, for your grant? You can't. So either you can say forever, or better to do some other kind of research, high-level simulation or something to establish an upper limit for it. Was that the only question? Fabulous. There we are. Well, thank you very much, folks. I'm sorry there are people who are already eating their lunch already, but hopefully there'll be some left. And thank you.